right? But it's a z-test. So again, you have HO, mu equals HA. Mu is either greater than, less than, not equal to, and your test statistic is z. If sigma is unknown, again, you have to assume normality. What test are you doing? Again, you have HO, mu equals, because we're doing means. HA, mu greater than, less than, not equal to. Test statistic changes to a T. If it's a proportion, that's a prop is proportion. Yeah, one prop z-test, but what is it? So it's a z-test, but what are your assumptions?
That your NP is greater than 10.
N times P is N greater than or equal to 10. It's really that's really a binomial, and you're using a normal approximation to that. To make sure it's large enough, that has to be true. So does N times Q has to be greater than or equal to 10. And if so, then HO is that P equals some number. HA is that P is either greater than, less than, or not equal to. Your test statistic is Z. For variance, what do I do for variance? Again, I'm assuming normality. HO is that sigma square equals something, right? Do we do single sample test for variance?
We use chi-squared, right?
That's correct. Then that means we did that.
Did we?
Did we? I don't remember.
If I say no, does that mean we don't have to do it on the exam?
I know we did 2 sample ones because we did F-tests. Right, where we're comparing 2 variances, we did F-tests, is that correct? Yeah, I know we did 2 sample ones. I thought we did those, but maybe not. Maybe we just did confidence intervals. Maybe I forgot to do this hypothesis test. But it's the same thing. I'll leave it there, but I'm not sure we actually did those. But I thought we did.
We did a bunch of chi-squared. We did a few at least. We did
The
a
hypothesis test for variance.
Like an TA before.
Oh, it's
It's the one that you have to do by hand because you can't do it on a calculator.
no, that's the confidence center.
No, because you did the
But you could do the you could do the, that's why, because you could actually do that up with a calculator. I might be wrong, is what you're saying. Those are all the 1 sample ones, and this one's questionable. I can't remember whether I taught this or not. So if I didn't, you're in luck. 2 sample hypothesis tests. Here's where it gets really gnarly, right? Because you got to deal with hypothesis tests that are independent, where you're talking about the difference between 2 independent means. Independent means. mu1 equals mu2. Again, you have to deal with the fact you know sigma. If you do, you're good to go. HO, mu1 equals mu2. HA, mu1 doesn't equal to, is less than, greater than. Again, could go eat all 3 of those things. Your test statistic is Z. If you don't know sigma, this is where it gets a little challenging. So you got to know, do I pool the variances or don't I pool the variances? Whoa, remember that? I think you had some homework over that, if I remember right. Pooled or unpooled? How do you tell the difference? You could do an F-test. What does the F-test tell you, though?
Tells you the ratio of the variance.
Right, so what does that tell you?
If one's exceedingly larger than the other, then they can't.
Okay, so if the variances are the same, you can pool them. If the variances are significantly different from each other, you cannot pool them. So when you're trying to make that decision of pooled or unpooled, if you know something about the phenomenon, then you don't have to go through all that. And there's a couple of general rules of thumb you can also look at too. The bigger variance shouldn't be more than twice the smaller one. or the smaller one should be less, right? The ratio should be either between 1/2 and 2. But if you know something about the phenomenon, you should be able to, and this is where it comes understanding your field, right? If you know whatever field you're talking about well enough to understand, should these vary, is it reasonable to pool these variances or not? If they're pooled, then the mean of look, I'm gonna write this over and over again. This is the same for all of them, that part. Your test statistic is Z. If they're pooled, you also have to deal with this SP square, where you actually calculate the pooled variance, or the pooled standard deviation. It's got this big long formula. If it's unpooled, same null and alternative hypothesis, your test statistic should be T. Why did I say Z? I'm sorry. Your test statistic will also be T, only it's got some weird formula for degrees of freedom. It's a great big long formula for degrees of freedom if you're not pooling them. Yep.
What does that say, difference between something?
Independent means. So I'm looking at the difference between two independent means. So the other way to, I formulate mine with just mu1 equals mu2. But there are people who formulate that hypothesis as mu1 minus mu2 equals 0. They're both essentially the same thing, right? Mu1 equals mu2 means that mu1 minus mu2 equals 0. That the two means are different or the two means aren't different, either one greater than or less than the other. Every once in a while, and I mean, you're talking about 3% of all hypothesis tests, they'll want a number, they'll say the difference is 5. Instead of 0, instead of the two means being equal to each other, they'll say they're different by 5. Then that number right there would be a 5. Then all bets are off in how you plug that into technology. But that's such a rare, that's typically the way that those are formulated. What if they aren't independent means? What if they're paired somehow, like you did a pre and a post test? So the other way we had the same thing, this is 2 samples there, 2 samples here would be a paired t-test. You have to have some reason to pair them. Right? They're the same location. You took samples from 100 different locations. At each location, you took 2 samples, one from the top of the soil and one from 10 feet below. You went to another location, you took a sample from the top and 110 feet below. You went to another location, you took a sample from the top and then 10 feet below. Each of those locations has a pair of samples, the top sample and the one from below. It wouldn't make sense to take all the top samples and put them together because they're not independent of all the bottom samples. Whatever that soil is made up of in each of those locations might have an effect on that problem. In which case, in that case, you have a paired t-test. And your null hypothesis is that the mean equals to some number, the mean of usually it's the mean of the differences. I'll put diff. Versus HA, that the mean of the differences is not equal to or greater than or less than, whatever the number is. This is a 1 sample t-test. It's just, that's mean of the differences. So that's where I'm going to take each of those 2 things and subtract all the differences, and I'm doing the hypothesis as on that sample of differences. I think the example we did in class was the 2 guns, right? We did the guns, we paired them by the person who was shooting the guns, right? And the first thing we did was subtracted them to see the column of differences. And that's what we ran our hypothesis test on, was on that column of differences. If they're the same, then the mean of the differences should be 0. Yeah.
So you're kind of effectively turning that 2 sample test into a 1 sample test?
That's exactly what you're
To
doing.
take the difference?
Yep, you're just 1 column of differences, that's right. 2 samples, we did 2 samples for proportions. For 2 proportions. Again, both n times p had to be greater than, for both samples, had to be greater than or equal to 10. HO was that the proportion of 1 equals the proportion of 2. HA would be either not equal to, greater than, or less than, depending upon which one you got. Your test statistic has to be Z. If it's not big enough, you can't do the problem with parametric statistics. You have to do non-parametrics. Proportion, what else did we do? 4 additions. We did 2 samples for variances or standard deviations. This is the F test. Yeah?
Are you saying, sorry, this is I guess going back, are you saying for the peer review test that that's a one sample?
That's correct. That's exactly what I'm saying. 1 sample of differences. Yep.
So what is SP under the pool thing?
That's the standard deviation, the pooled standard deviation. Rather than using the individual ones, you have to calculate. You don't have to calculate, your calculator's gonna do it for you. But the reality is, when you get out into a field, and look, you're gonna go be on the floor at Boeing, you aren't gonna have your calculator in your pocket.
You don't know.
Maybe.
Well, you might have your calculator, I mean, y'all are nerdy enough that that might be true, but chances are you aren't gonna have your calculator in your pocket. But what you are gonna have to be able to do is talk about, am I pooling something or not? Are you pooling variances or not, and why? Based on whatever process you're working on. That's the piece you cannot screw up. You know, and I don't mean to trivialize the calculations, because I mean, a long time ago people had to actually calculate this stuff by hand. But the reality is you live in 2019. Things are different from you than they were in 1950. You do have technology that's doing that for you. And the danger is you get complacent about the technology giving you right answers without really thinking about what those answers mean. I don't care if you ever calculate by hand another number again. What I do calculate is every single time a black box spits some numbers out at you, then you think about what does that really mean. And I mean every black box. Think about, anybody ever work out at the gym? On a treadmill?
Once.
Or a whatever machine, cardio machine? You believe that thing, right? That you burn that many calories. Now, some computer programmer programmed that. I did a project once for Microsoft where I actually looked at that was back when Xbox and the Kinect thing happened, right? They had the little thing. And they wanted me to think about how I'd use it in a curriculum. So I made my, for at that time I had a teenage daughter, and I said, okay, we're gonna figure this out. We had that dance game. You know what I'm talking about? You're all young enough to know this, right? This, whatever. And so I made her dance and dance and dance, and all of a sudden the screen flashed up at the end. I thought, well, that's just a bunch of data. Why can't we harvest all that data and then reverse engineer whatever the computer programmer put in there to make it show how many calories burned there was? And I took it to Microsoft. Microsoft went, oh man, I hope they did it right. Right? Because some guy sitting there coding some stuff wrote that code to do that. A treadmill's the same way. When you go on that treadmill, somebody coded it to give you, when you put in your weight and your age, to give you an answer for how many calories you burn based on how far you ran on the treadmill. How do you know it's right?
It's not.
You're trusting that guy that, or woman, whichever, that person that coded that thing. You have no, you know, say the little thing you wear on your wrist. Right? And sooner or later, you're going to be doing that for some device that you create. And people are going to be trusting you. People are going to be, because you're going to invent something cool like that, and people are going to be trusting that your machine, your black box, has the right stuff in it. So make sure it has the right stuff in it. Variances, HO, that the variances are the same. HA, that they're different. Usually it's just strictly different, but you could be greater than, could be less than. Your test statistic is F. Again, you got a button for that. What else do we do? Is that it? And then we also had, so it's not, well, I guess it is well, it's one sample, but it's 2 variables. We had ANOVA. When you're testing the difference between lots of means, more than 3 means, again, you have to be able to say they're independent of each other, and that they are normally distributed, and that they have the same variance. Those are the assumptions you're making. And then we did, the last hypothesis test we did was hypothesis test for slope. That's not everything we did, that's just the hypothesis test. Right, exactly, there's more stuff on this test than just hypothesis test. Yes.
Wait, are we not meeting on Thursday?
Yeah, we're meeting on Thursday. I just figured I'd start reviewing right now because I had some extra time, but I'm gonna be done in just 2 seconds. And you're gonna be out of here. This is also an F, by the way. This is a T. And look, that's just the hypothesis you do in undergraduate statistics. Guess what? There are like a billion more out there. Exactly. You need to think about what you're doing in every problem, and if what you're doing doesn't fit in the assumption. Thanks, Eric. That was right in the way of what you just took your picture of.
No, I got it for you, man.
Did you get it? Okay. The reality is, if what you're trying to show doesn't fit there, if it's breaking an assumption like the normality assumption or the equal variance assumption, you got to find something different. You can't use that hypothesis test. No matter how bad you want to shove stuff into an ANOVA table, not everything fits in an ANOVA table. You have to check the assumptions first before you do that. Because I guarantee you, if it doesn't fit, there's a different test that does fit. It just means a little Google or a little call in a stats department or calling your favorite stats professor and saying, hey, I got this problem, I can't figure out what test I should use. Right? I have people do that your other faculty member called me and say, hey, I'm trying to do this thing and I can't figure out what test to use. That's my job, okay? You call me up. And then what I do is I say, I'll tell you, but you have to come speak to my class.
I have a question and a half.
Yes.
Under ANOVA, does it say the test statistic is F or?
Yes.
Okay, and then also I found what we did on chi-squared. So you gave us for sigma squared and then you gave us for sigma and we did a bunch of
But
practice
that's just
ones,
confidence intervals,
and
right?
then you gave us this one. Oh, is it really just?
Yeah, I don't think I did.
Yeah.
After thinking about this, I don't think I did the hypothesis test.
Never mind.
You didn't.
Huh? Sure, you can rule that one out for the final, so we've determined that this didn't happen. I forgot it.
I'm just gonna state right here, but more than 3 means, or are you just saying 3 or more?
Or 3 or more,
Okay.
3 or more, I'm sorry, yeah. So I had more than 2, more than 2. Questions? Okay, yep. The assumptions for ANOVA, they have to be independent, have to be normally distributed, and the variance have to be equal. All right, so tomorrow, today, as soon as I get back to my office, I'm going to put up a review sheet. Look, this has been a challenging quarter in terms of, and for all of us, spring quarter always is. Spring quarter, because you always